Dear students, in today's lecture we will study about the rotating magnetic field, winding insulation in an AC machine power flows and losses. Then at the end we will talk about the voltage regulation and speed regulation. First of all, the rotating magnetic field. In this section we will talk about how can we generate a rotating magnetic field. As we seen in the previous lecture, the three voltages with different phases of 120 degrees were shown as VA, VB and VC. But we have seen that they were generated after the induction because of the current. So there were three loops in the stator. One was AA bar, another was BB bar, and the third one was CC bar. Now we will see this in detail. What happens if three-phase set of voltages are applied to the three windings of the stator? So we have three windings as I have discussed earlier, and in these three windings a set of voltages, these voltages are applied. Now the case is reciprocal. In this case the three set of voltages are applied, which is the fundamental principle of AC machine. The rotating magnetic field concept is illustrated by an empty stator containing just three coils. This is the empty stator. This is the first coil AA bar. This is second coil BB bar, and this is another coil CC bar. All these coils are 120 degree apart from each other. Since these windings produce only one north and one south magnetic pole, that's why it's a two-pole winding. Now we apply three different currents to the stator of the machine. All these three currents are out of phase with 120 degree, and then we see what happens to the stator at different angles. The three phase currents are given by the equations in which Im is the magnitude of the current and sin omega t is the sinusoidal part of the current equation. This is for AA bar loop or winding. Then we have BB bar and CC bar. All these three are 120 degree apart from each other. But this current produces magnetic field intensity, which has been shown by H AA bar, H BB bar and H CC bar. It can be seen from the figure. If this is BB bar, then its magnetic field and flux would be perpendicular to the line of BB bar. Similarly, the HAA bar is perpendicular to the line connecting AA bar if we see the loop from the top. Same is the case with the CC bar. But we know that resultant flux density is equal to mu of H. So B is equal to mu of H. So by applying this formula to these three values of H, we can easily find B, which is the resultant flux density for the three cases. The rotating magnetic field, as we discussed previously, that we will calculate this magnetic field at different angles, at different omega t. So if we put omega t 0 in this equation, we will get sine 0, and after getting sine 0, the whole answer right hand side would become 0, as you have seen in this case, first equation for the BAA bar. But in case of BB bar, omega t is putting omega t equal to 0, we will get sine minus 120 degree with 120 degree of angle. If we see the case CC bar, then there would be minus 240 degree with 240 degree of angle. Now the next step is to get the B net value of flux density by adding all the three flux densities. We will get B net at omega t is equal to 0 degree, which you can see is shown in this yellow portion of the slide, that B net is equal to B AA bar plus B BB bar plus B CC bar. After opening the values of B BB bar and CC bar in terms of sine theta and cos theta, after using these values, under root 3 over 2 BM and with angle of 120 degree and 240 degree, so it can be derived in the terms of cos and sine theta, and then adding them and getting the answer would be something like this. And this can be consulted from the book, where this derivation has been explained in detail. So these are the directions of BB bar and BCC bar, and this is B net, and there is no BAA bar, since BAA bar is 0, and this, let's suppose this is BB bar, loop BB bar. It can be seen that BB bar, from B the current is coming out of the paper, and at the point BB bar it is going inside the paper. Similarly, in CC bar, from C bar it is coming out of the paper, and at the point C it is going inside the paper. So this is the diagram for omega t is equal to 0 degree. Now we calculate the value of flux densities at omega t equal to 90 degree. As you can see that by putting omega t is equal to 90 over here, we will get sine 90 degree, sine minus 30 degree in second equation, and sine minus 150 degree in third equation. Similarly, we can also calculate the B net by adding them together. The pictorial view of these flux densities can be seen from the right figure, and this figure shows that the direction of B AA bar is towards right, B BB bar is slightly downwards, and B CC bar is slightly upwards, and the B net is in the direction of right, and this can be calculated by adding all the three flux densities. So this is at omega t is equal to 90 degree. It can easily be extended for omega t is equal to 180 degree and omega t is equal to 270 degree. So the direction of B net changes, but magnitude remains constant, as we have seen from the previous 4 cases, and the net magnetic field is rotating in a circle. As we have seen, the angles are different. The rotating magnetic field in the stator can be represented as rotating north and south poles. So these north and south poles are rotating in the stator. So the lines are going out of the north and going into the south. Where the flux line leaves is denoted as north pole, and where it enters is called south pole. So flux leaves from north pole and enters in the south pole. When the electrical cycle, so this is a one cycle. When the electrical cycle of the applied current completes one rotation, the magnetic poles also complete these magnetic poles also complete one mechanical rotation. That's why the mechanical speed of rotation of magnetic field in revolution per second is equal to the electric frequency in hertz, and can be written as, since they are equal, so electric and mechanical speed are equal in the case of two poles. The windings on the two-pole stator occur in the order taken counterclockwise: A, C bar, B, A bar, C, B bar. This is like, this is point A, then this is C bar, then B, then A bar, then C, and then B bar. They are taken as counterclockwise. If this pattern is repeated twice, then we will have a situation like this, as you can see in the second figure, where all the points are repeated again. When three-phase current is applied, two north and two south poles will be created because of the additional repetition of the winding pattern. A pole moves only halfway around the stator surface in one electrical cycle. So this is two north and two south poles in this case. And a pole moves only halfway around the stator surface in one electrical cycle. That's why the relationship would be electric frequency of the current is twice the mechanical frequency of rotation. So it would be 2 of theta m. Theta of E is equal to 2 of theta m. Similarly, F of E is equal to 2 of Fm, and omega E is equal to 2 of omega m. Because of the halfway around stator surface, the pole moves in an one complete electrical cycle. So it can be deduced that if P are the magnetic poles, then P by 2 are repetition of windings sequence around the inner surface of the stator. Then the electrical and mechanical quantities on the stator are related as theta E is equal to P over 2 theta m. Let's suppose P is 2 poles. If it is 2, then 2 over 2 would become 1, and theta of E is equal to theta of m. Let's suppose poles are 4. Then 4 over 2 would be 2, and theta of m would be theta of E is equal to 2 theta of m. So for the any number of P, it can be calculated the relationship between electrical and mechanical quantities on the stator. The electrical frequency in Hertz can be related to the resulting mechanical speed of the magnetic fields in revolution per minute. If there is a case, if Nm is revolution per minute, then if we know the value of Fm, we can substitute this Fm value in the equation Fe. We will get P over 2 into Nm over 60. For calculating this equation for Nm, we will get Nm is equal to 120 of Fe over P. Now we want to see the winding diagram. This is the winding diagram with 4 poles. Now we see from its inner surface, showing how the stator currents produce north and south magnetic poles in this stator. So these are the points 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 and 12. This is A1. If we move counterclockwise from left to right, this is A1, as you can see from here, going into the paper. So this is again going into the paper. Then we have C2 bar going into the paper, B1 coming out of the paper, A1 bar, this point coming out of the paper, C1 coming out of the paper. Similarly, it can be calculated for all the points, and it can be seen how the current is circulating in these coils and windings, and how the magnetic fields are produced at different points. So 4 poles are produced, S, N, S, N, as you can see in this diagram. Now we want to know that whether we can reverse the direction of the magnetic field or not. Yes, we can reverse the direction of the magnetic field by swapping the current in any of two coils. So if we swap the current in any of two coils, the direction of the magnetic field will be reversed. Similarly, it is possible to reverse the direction of rotation of an AC motor just by switching the connection on any two of the three coils. Now we come to know about the insulation in an AC machine, a winding insulation. The winding insulation is one of the most critical parts of an AC machine design. If this insulation breaks down, the machine will be shorted. Overheating due to high winding temperature is one of the most common reasons for the insulation breakdown. Now we will know how can we prevent the overheating. The overheating can be prevented by limiting the winding temperature by providing cooling air circulation in the machine. The increased temperature will not cause an instantaneous winding breakdown, it will rather decrease the overall life of the machine. Now we will see about the chart, or you can see a graph which will relate the insulation life and winding temperature for different classes of the wind insulation classes. So on y-axis you can see that this is insulation life. On on x-axis you can see this is winding temperature. From right to left, on the x-axis the temperature is increasing from right to left. So it can be seen that for the lower winding temperature the insulation life is larger. So the insulation life can be prolonged by reducing the winding temperature. The four lines show about the different classes, as you can see, class A, B, F and H. But one thing can be noted, that the behavior of all the four classes is almost similar. Machines, power flow and losses. AC generators take in mechanical power and produce electric power, while AC motors take electric power and produce mechanical power. In either case, not all the power input to the machine appears in the useful form at the other end. There is always some loss associated with the process. As we know that efficiency represented by eta in this case is equal to output power over input power, and the equation can be written in the form of output power and power losses, input power and power losses. It can be written in any form. So if we take this equation, it can be further simplified as 1 minus P losses over P in. But as we know that we come across a number of losses, and we also discussed these losses in previous lectures in details. So these are a few losses written in the form that there would be some copper losses, two types of copper losses, armature losses, field losses. So these are basically four types of losses which we discussed. As we input some power, there would be losses and the whole power would not reach the output. So we can see from the phase AC generator power flow diagram that mechanical power is input, and then a number of losses are experienced, and then the power is converted from mechanical to electric power at this point. But even after conversion, this power would not reach the output point. There would also be some losses after the power is converted from mechanical to electric power. So these are basically I square R losses, armature loss, armature plus field losses. So these losses are experienced even after the mechanical power is converted to electric power. So the output power would be something like this. Now we see the phase AC motor power flow diagram. In this case, the electric power is provided at the input and it is converted at this point, and after conversion from electric to mechanical power, still there would be some losses which are experienced over here in the form of core losses, mechanical losses and stray losses, and after which the remaining power would reach the output in the form of mechanical power. So this case is basically reciprocal to the previous case. Now we talk about the voltage regulation and speed regulation. We already studied about the voltage regulation, but now we will also study a speed regulation. So in the case of generators, the generators are compared with respect to their voltage regulations. So voltage regulation for a generator is the measure of its ability to keep a constant voltage at its terminals as the load varies. So VNL represents no load voltage and VFL represent voltage with full load. So this is the formula for voltage regulation, and this is the ability of a generator to keep a constant voltage at its terminals as the load varies. But in the case of motors, there is a speed regulation, which is the ability of the motor to keep a constant shaft speed as the load varies. Both these scenarios can be compared in this slide. On the left part, you can see that AC motors are compared by their speed regulations. On the right side, you can see that the AC generators are compared by their voltage regulations. So speed regulation, the formula for speed regulation also shows the omega NL and omega FL. This is the omega or speed for the no load and speed for the full load. Similarly, VNL is the voltage for the no load and voltage at full load. So assume the motors are run from a constant source Vt unless the voltage change is specified. In the case of generators, they are run from a constant speed source called prime mover unless speed change is specified. So dear students, this is for today. Thank you.